Hello, today we're going to look at the particle in the infinite square well, or also known as the particle in a box. Okay, so this may take a couple of videos, alright? So we're going to go straight into it. So a square well is a potential that forms a square shape, alright, which we have here. This is our potential well we'll be dealing with. So we have our potential energy on the y-axis and our distance x on the x-axis. So down here we have some constraints. So we see that the potential Vx goes to infinity where x is less than 0. Okay, in other words, this area here. We have our potential energy where our particle is, okay, within the square well, is 0, where x is between 0 and a, okay? And we also have our potential energy goes to infinity again, where x is greater than a, okay, here. So our particle is trapped in this infinite square well, where our potential energy is 0 inside it, okay? So, using square wells, you can trap particles, like I just said. If you put a particle into a square well with a limited amount of energy, it will be trapped because it can't overcome the infinite potential at either sides of the square well. Okay? Therefore, the particle has to move inside the square well. So you may be thinking, does the particle just sort of roll around on the bottom of the square well? Not exactly. The particle is in a bound state, okay? A bound state is simply a state where the particle can't overcome infinity. And its wave function of the particle, okay, depends on its energy. The wave function isn't that complicated. Here it is. Okay, psi of x equals the root of 2 over a sine n pi over a x for our states 1, 2, and 3. Okay? So you have the allowed wave functions, okay, here for the states, but the energy of the allowable bound states are given by the following equation. Okay, this is the energy for the allowable bound states. E equals h bar squared pi squared over 2ma squared n squared, okay, where n is of course our quantum states. So this equation implies that the particle can only occupy certain energy levels, okay? The energy comes in discrete energy levels, okay? So, there you have it. That's the overview of the infinite square well. Okay, so now we're going to deal with the Schrodinger equation, and we're going to derive, well, over the next couple of videos, we're going to derive the wave function and look at the energy levels, okay? So, the Schrodinger equation, okay? You may remember, it looks like this. We have minus h bar squared, okay? Divided by 2m, okay? And then we have the Laplacian operator, okay? Or just the second order derivative of our wave function, psi r, plus Vr psi r, and this is equal to E psi r. Okay, so the Schrodinger equation looks like this in 3 dimensions. Okay, writing out the Schrodinger equation gives you the following. Okay, in 3 dimensions, we simply have this. Okay, the derivative in each of the coordinates, and finally z. Okay, and then we add psi r, it's acting on psi r, and then we add to that Vr, which is our potential energy, and psi r, alright, that's equal to E psi r. Okay, that's in 3 dimensions. Alright, so you're interested in only one dimension, the x distance, okay? Because our well is only in the x distance. Okay, so therefore we can rewrite the Schrodinger equation in this very basic form. Okay, we have minus h bar squared over 2m. Okay, and then it's simply the ordinary derivative, okay, with respect to x of psi of x plus v of x psi of x. Okay, like that. Alright, so because the potential energy inside of the well is 0, okay, the Schrodinger equation simply becomes this. Okay, remember in our potential well, the potential energy is 0. Okay, this is where the particle is. Therefore, if the potential energy is 0, we can write it as this: minus h bar squared over 2m. Okay, then we have our derivative, and okay, that becomes 0, so we just equal to e psi of x. Alright. Okay, so, and in problems of this sort, the equation is usually written as this. Okay, this makes it look slightly more simpler. We have ordinary derivative, okay, and then we have psi of x, but what we do is we add k squared, okay, psi of x equals 0. Alright? Okay, so k squared, okay, what is k squared? K squared is equal to 2me, is the mass, divided by h bar squared. Okay, k is the wave number. Okay, remember we're dealing with wave functions. So now you have the second order differential equation. Here it is, the second order differential equation to solve for the wave function, okay, of a particle trapped in an infinite square well. You get two independent solutions, okay, because this equation is second order differential equation. Remember, this is also the differential equation for the harmonic oscillator. You should know that the solutions of this differential equation are this. Okay, we have two independent solutions, alright, and they are psi 1 of x, okay, our first solution is equal to a sine of kx, and then we have, 2 of x is equal to b cosine of kx. Alright, that's an x. There are two independent solutions to this differential equation inside the square well where the potential energy is 0. A and B are constants that are yet to be determined. Okay,